Okay, thank you so much for coming or for watching this video on topology. So we are continuing with geometric topology. We're already week 9. Time really flies like an arrow, and yeah. So as a reminder, what we have seen and what is kind of really crucial, and we will wrap up the rest now, is that we want to determine surfaces up to homeomorphism. So we want to determine what surfaces are homeomorphic. And we have seen two kind of really cool ways to distinguish them, namely by counting problems. So we count the number of boundary cycles or circles, and we count the Euler characteristic. And both of them are just essentially integers. So the Euler characteristic is an integer, and this is, of course, just a natural number. So that's essentially enough to distinguish surfaces. Not quite, there's a little bit missing, and that's exactly what we will discuss in today's lecture. So kind of the missing piece. We do a bit more, but that's kind of the crucial information. So we're discussing, well, what is missing to completely determine the surface up to homeomorphism. So kind of to answer our question. Yeah, so the point today will be to address that problem. Okay, so we want to address the problem of answering how to determine surfaces. I won't state it today, but we will get there. I'll just give you the third notion. So something is missing here. So we have 1, 2, and something is missing 3. And as soon as we have to check 1, 2, 3, we have checked. Well, we can kind of determine the homeomorphism class of surfaces. Yeah, so let's do it. Let's go ahead. So these two invariants, we call them invariants, remember? They are kind of easy to compute. We'll do that several times, but they're quite not enough. That's exactly the point. There's the one information missing. And here was one example. So on the right-hand side, there's a torus. Remember that we kind of wrap the torus by putting it into a cylinder, and then we take the cylinder and wrap it around into a torus, right? So then we identify those two edges. Then we get rid of the squiggles here. And it turns out that the Euler characteristic, remember that was chi, of this piece is 0, okay? And whatever is on the other side, it's not quite clear how we can decide this, but it turns out that the Euler characteristic is also 0. How do we do that? Well, we just look at the number of vertices that we see, and in both cases, there's just one vertex. So here, for example, this vertex is at the head of A, so it's here. So it's the tail of B, so it's here. So it's the head of B, so it's here. It's all the same vertex. So we have one vertex, and in both cases, we have two edges, and the face is staring right at us. So the Euler characteristic is 0 in both cases. And they both don't have any boundary cycles, so they also have the same number of boundary cycles. So how can we distinguish now those surfaces? And I cheat a bit. I tell you they're not the same, but right now those two informations are somewhat not enough to distinguish those two surfaces. So what is the right surface? Can we somehow determine that? And what is missing here is the following ingredient. And I give a slightly weird definition, but it turns out that it's kind of a good definition for combinatorial practices. And after we discussed it a little bit, I will show you kind of the geometric, if you want, interpretation of that definition. Very often this works the other way around. So people give the geometric one and then deduce the combinatorial one. But I would like to stay with the combinatorial one because in the end, we want to study polygons and not anything else than polygons. Or we want to use polygons to study higher dimensional objects. Okay, and the notion we need is this notion of orientability. So maybe I use a slightly different color here. It's difficult to see. Whatever. And the surface is non-orientable. Let's use a different color. And otherwise, it's orientable if it contains a Mobius strip. Okay. If it does not contain a Mobius strip, it's orientable. It's kind of a really strange definition, but it will turn out to be a really good definition, which is really not clear right now. So right now, you should kind of wonder a little bit, how on earth do I even check that? Whether a surface contains a Mobius strip or not, or what does that mean? Can we actually use that in any form. Turns out we can, but right now it really looks like, as I just said, it really looks like there's just no hope. We could say anything here essentially. But we will see that this one is super easy to check. So Euler characteristic is computation, number of boundary cycles is a computation, and this one you can just check by looking. But right now, just from the definition, that's not really clear. Yeah. The only thing that is clear is that the Möbius strip is non-orientable because the Möbius strip contains a Möbius strip. Yeah, but right now we don't have any other examples. I will show you two more examples. Then I will comment on what this definition actually means. Where does it come from? Why do we want it? And then, yeah, so then the lecture is already over for today, but eventually we'll see that this is a missing ingredient to get our complete list of what we need to check whether two surfaces are homeomorphic. And we also see a very, very, very explicit criteria to determine whether a surface is orientable or not. Right now, this is our definition. A really strange definition, as I said. And just combinatorial, it's just in practice, it's just fantastic. That's what we will see. But it's kind of a little bit, it's not quite clear to me why I would define things like that. Anyway, hopefully it's clear why the Möbius strip is orientable. But our other friends, all of them, or the standard surfaces, the sphere, the annulus, the disk, the torus, projective plane, and Klein bottle, are they orientable or not? Doesn't seem to be super clear. We'll discuss two of them in a second. And even this is not clear. It could be that we want to do this on a polygon decomposition, and it could be that this depends on the polygon decomposition of the surface. This would be extremely bad. It's not the case, but right now from the definition it could be, but this would be like extremely bad, right? Because we are trying to kind of find a criterion to determine homeomorphism classes of surfaces, and if we use something that depends on the polygon decomposition, then we are kind of fucked here. This would be really bad. Luckily, it's not the case. I just mention it right now because from this definition, it's absolutely possible that could happen. I hope that's reasonably clear. Okay, let's do an example. So the Klein bottle. So let me pull up the Klein bottle again. So the Klein bottle was the following surface. As soon as it loads, it was this funny surface. Let's start from the beginning. We take an annulus, and then we kind of glue the ends together in the twisted way. And that's why we end up with a slightly funny looking surface. Okay, let's do it again. We take the annulus, and we glue now the ends together, not as for the torus, but in the twisted way, and we get the Klein bottle. We can also see it here. So if you just glue together those two edges, then that's the annulus, but now we need to glue those together in a twisted way, and this is exactly where this twist in the animation comes from. Anyway, question here is, does a Klein bottle contain a Möbius strip? And it does. So let's try to see that. And I show you kind of the way we can determine this right now, and later we'll see a much better way. But for now, the only thing we can do is we can try to find it by massaging our polygon decomposition a little bit. So I just, cut it and draw two extra lines. It's still the same. I just have now a green arrow and a red arrow. I didn't do much. I just put them there, and we can now think of it as being cut at those lines. Nothing happened. And I subdivide my edges here on the side. So I put in those middle things, but that's again nothing. I really just subdivided my surface, and it's really just still the same information. It should always be the same information because I want kind of to massage the Klein bottle. And now comes some of the main trick. I take this picture, and this is a bit difficult to see, but let me just do it. And I move the green arrow up so that the green arrow is at the top, and because that's how it works, at the bottom at the same time. I just take my picture and wind it a little bit up, right? So this thing here now ends up here. As you can see, here's a red one, and the top one then moves to here. I just winded it around. That's all I did. I just took a little bit different perspective on my piece of paper. I winded it around, And now something funny happens. So no change. I just changed, just wind it around a little bit. Now the top part, if you cut it off, is actually a Möbius strip. How can we see that? Well, let me just redraw it. This is this top part here. So it has a red edge at the bottom. It has a green edge at the top. So they are non-paired. So you could call this B and A, for example. What was the other one? Red. And then there's a purple edge on the side. Do I have some nice purple here? This is more bluish, but anyway. Yeah, there you go, purple. There's this purple edge on the side. Let's call it C and C. And this is exactly the Möbius strip. So let's go back. I had the Möbius strip here, and we'll see the Möbius strip several times. Well, it has a different labeling, and it's on its side, but it's really the same. So you have two free things, and one that is glued together in a twisted way, right? So this is this twisted gluing here along A. You see the Möbius strip in the second one. So I actually found a Möbius strip up here. And it turns out that I can also find a Möbius strip down here. This is also a Möbius strip. So let me draw it again. Now, without colors, maybe. So here's A and B. Let's call this A, let's call this B. And here's an edge that goes upwards and is identified with the edge that goes downwards on the other side. So I've cut the Klein bottle into two pieces, and both of them are actually Möbius strips. Okay? So the Klein bottle contains a Möbius strip, actually two of them, but it contains one, and it already makes it non-orientable. Okay. So that wasn't quite trivial, but let's have an animation to see that it actually works. So what you see here in the front is a Möbius strip. So here the green goes onto the orange, and the orange is now in the back and then comes up in the front again. So that's really a Möbius strip. Similarly, in the back you have a Möbius strip. So in the front you have two Möbius strips, as in my little picture before. And now you can just fill in the space between them, and what you get is really a Klein bottle. So a Klein bottle is just two Möbius strips glued together if you want. So you just fill in the space in between, and you get a Klein bottle, right? And this is exactly what I did here on the polygon. I've colored it into two Möbius strips. Hope that makes some sense. Okay, this means the Klein bottle is not orientable because we actually wanted to. So the Klein bottle is not orientable because we had this definition that as soon as it contains a Möbius strip, it is not orientable. So Klein bottle is not orientable simply because there's a Möbius strip. But it was a bit difficult to do that. So we certainly need a better way of doing it, and we will get a better way of doing it. So you never need to do this by hand. I'm just showing you right now how this looks like, how we can cut out Möbius strips out of various surfaces. So sometimes the Klein bottle, as I just showed you the animation, the Klein bottle is a Möbius strip and a Möbius strip glued together. Okay, let's do another one. The projective plane. Projective plane looks very similar to the Klein bottle. Here the Klein bottle has two twisted edges and two edges that point in the same direction. And here just everything is twisted. So the Möbius strip, or the the projective plane is completely twisted. So you need to glue it together twice twisted, which is like, why is this so difficult to imagine? In about 20 minutes, we'll see why those surfaces are so difficult. I kind of prove that for you in some sense, and why they don't appear in nature. But for now, let's just do it. So I kind of cut it now, like cutting off little triangles here. So here's a little triangle, and here's a little triangle. Nothing changed. I just cut it a little bit and made it kind of finer, decomposition finer. And now I turned it. So this one here is here, and this one here is here. And whatever is here in the middle ends up here in the middle. Okay, so I just turned it around. Nothing was kind of easier to illustrate. But at the top we have a triangle, and at the bottom we also have a triangle. So let's have a look at the triangle. So let's do the bottom triangle, for example. The bottom triangle has this edge, and then an orange edge, and then a green edge. In particular, all edges are free, and so this is just a disk. And similarly, the top triangle, everything here is kind of free, so this is just a little disk here. Yeah, and what is the middle? Well, let's have a look at the middle. So here, our little middle is, it has a green edge and a red edge, and the other one is a bit difficult to see, but it's actually an orange edge. And the orange edge is twisted. So that's our little Möbius strip again. So this is our Möbius strip. And the opposite is clear. So I cut the projective plane into two disks and a Möbius strip. So the projective plane, if you want another way of viewing what a projective plane is, you take a Möbius disk, a Möbius strip, it has a boundary, and you just glue a disk into the boundary. And whatever you get, really difficult to imagine, is a projective plane. I hope that makes sense. Okay. And in particular, there's our Möbius strip here, right? So it's not oriented. Projective plane is also not oriented. And whatever. Maybe this one is a Möbius strip without a boundary. So kind of both of them are a Möbius strip without a boundary, but somehow in a different form. So Klein-Bodl is two Möbius strips glued together, and the projective plane is a Möbius strip with a disk inside. So you just fill in the whole of the Möbius strip with a disk. Okay, but anyway, so we have now verified that, come back to our definition, the non-orientable, that two of our favorite surfaces, the projective plane and the Klein-Bodl, are not orientable. So what about the others? And how can we even decide anything? That's kind of really difficult to see from this point of view. So these are non-orientable, and O, and the other ones are orientable. Okay. Goes on and on and on. Fine, good. Okay, let's go on. So, and in order to answer that, we kind of need to address the question, what does it actually mean? I mean, it's kind of a definition, fine, but whenever you see a definition, it is really, really helpful to ask yourself the question, why on earth would we define that shit? So definition, you can essentially define everything you want. So, but some definitions are good and some definitions are bad. So this is a good definition. So let's understand why this is actually a good definition. It's a combinatorial version of the notion of direction. Okay. So I will tell you now how that works. It's really beautiful. And I have some hopefully nice pictures and animations for you. So what is direction in one dimension? Well, it's really just whether you go right or left, right? So if you have one dimension, what can you do? Well, you can start somewhere and you can go right. Or you can start somewhere and you can go left. So you have two directions, and let's call them, well, plus or minus, for example. So it's a yes or no, right? It's 0 or 1, so whatever you want. But you have two directions, you can go right or you can go left, right? So that's what you can do in one dimension. There's not much you can do in one dimension. Yeah, sometimes I think it's kind of really lucky that we don't live in one dimension. One dimension would be a little bit boring, I guess. Anyway, we want to generalize this to higher dimensions, but in a not quite straightforward way. We'll see that there's actually a natural generalization, but it's not now about the walking directions, because that would be dimension itself. So if you would say now, okay, we can walk like this, 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 or this, then we have just discovered the second dimension, because that's what makes the second dimension. And so no, that's not what we want to do. We want to do something slightly different. Okay. We want to have a notion of left and right in 2 dimensions, and then in 3 dimensions, 4 dimensions, whatever, we'll see. And we do the following. We have a notion of rotation in 2 dimensions. We can rotate a vector. So here, if you want, we can move a point, and here we can rotate a vector anti-clockwise, or there's the other one, we can rotate it clockwise. Well, plus and minus again, 0 and 1. We can rotate a vector clockwise and anti-clockwise in 2 dimensions. I hope that makes some sense. 3 dimensions, higher dimensions, we'll see what I mean in a second. But this is kind of the picture I have in mind. So I have a left and right thingy in 1 dimension, because essentially there's not much I can do in 1 dimension. But in 2 dimensions, we have this notion of rotation clockwise and rotation counterclockwise, anti-clockwise, whatever you want to call it. Okay, and this is how it works. Generalized direction is the following. You choose an ordered basis. We'll do several examples in a second. So the basis of our space, but not just any basis, we want it to be ordered. So I really read first entry, second entry, third entry, up to whatever entry. This is an ordered basis. And I put the basis in the matrix. Just put the first basis vector in the first column, put the second basis vector in the second column, put the nth basis vector in the nth column. And the determinant of that, some number, the some real number, whatever it is. Okay, fine. The determinant of this is some real number. And the question about orientability is essentially the question whether this number is positive or negative. So we compare the standard basis with our ordered basis, and we do that by putting the ordered basis just in the matrix, just one by one, column by column, and compute its determinant. I will have the examples of one-dimensional and two-dimensional in a second. And we care about the sign of the determinant, not the specific value of the determinant, only the sign itself. Okay, so in one dimensions, for example, we compare B with E. So here's our chosen one, B, and here's our fixed one, E. So the E is always the standard one. It's always 1, 0, 0, 0, 0, 1, 0, 0, 0, and so on. Just the usual coordinate vectors. And the sign of this matrix is negative, as you can see, because it's pointing in the opposite direction. And if it points in the same direction, so here's our B again, and now it points in the same direction, then the sign is positive. So this is kind of a measurement whether we are kind of following the same direction as our standard basis, the EI, or whether we're following a different direction as our standard basis, and depending on the sign, plus or minus. In two dimensions, the same happens. So our standard basis, I make another picture next to here. Our standard basis is this one, just the usual, well, X and Y coordinates. And our B basis could be, for example, here, B1 and B2. And you see they are oriented in a different way, in the sense that here I go from E1 to E2 in the anti-clockwise direction in the fastest way. And here I go from B1 to B2 in the clockwise direction. And again, in the fastest way. I want the smallest angle. I'm not going around on the outside. I want the smallest angle. And that's why this is oriented in the opposite convention than the standard basis. And indeed, our sign gives us -1. So that's what this determinant is measuring, the sign measuring. Whether our choice of coordinate system, so the B's are just a choice of a coordinate system, is oriented in the same way as the standard one. And we do that, again, we can do it this way around. So let me redraw it. So here's E2, here's E1, right? The standard choice. And now let's say B1 goes like this, and B2 goes like here. So in this case, both of them kind of walk in this direction from 1 to 2. So in this case, the sign is positive and they are oriented in the same way. And you can imagine now something similar happening in higher dimensions, where you have a higher dimensional coordinate system and you wonder whether it is somewhat oriented in the same way as your preferred coordinate system given by the B's. So the E's are the standard coordinate system, and our preferred coordinate system are the B's, and we want to compare them to one another. Hope that makes some sense. And the determinant does that, and there's a plus and a minus, whether it's kind of has the same orientation or whether it has a different orientation. Okay, and what we do now, and this is somewhat better to explain in the picture, is the following. So on a Möbius strip, the following would happen. So let's say we have a Möbius strip and we have an ordered basis of our space on the outside, R3. So what we can do is we can somehow have some point M somewhere, whatever, let's say here, such that the third one is just orthogonal to the other one. So the cross product just means that the usual right-hand rule, so one of them is pointing orthogonal to the others. But the point is we can't do that consistently around the Möbius strip. Because if this kind of now points outwards here at this point, so let's say we have fixed start here, we do this here, so our vector points outwards, and now we turn around, walking around continuously, then eventually the vector will be here in the back and will point inwards. So we kind of get a contradiction. So we cannot continuously keep the orientation of our coordinate system as we walk along the Möbius strip. I will have the following animation for you. Hopefully that makes it somewhat clearer. Okay, let's do it a little bit bigger. So I want, at every point, I want a vector pointing in some direction. Okay, and we start with the annulus. That's the first picture. Let's go back to normal. And here everything is good. So everything points outwards, but for the Möbius strip, which is this twisted guy, so let's go back to the twisted one. We have this problem that if you go around, then we cannot change the direction where we look into. And that's called non-orientable. So we cannot choose consistently a coordinate system. If you move around, it will always come out with the opposite side. It will always come out twisted. I have several other animations for you in a second, but I hope that makes some sense. So I have here my Möbius strip, and I have something here that points in a certain direction that we choose. That I move along the Möbius strip, and the Möbius strip does this funny twist. And as soon as I hit this point again, this vector will point in the opposite direction. So I can't do that consistently. But if I think about the cylinder, not the Möbius strip, then it's really easy. We could just, we had it in the animation, it could just point outwards. It moves around, it will still point outwards. It will now be in the back and point in this direction. It will come back and point still in this direction. So on an annulus, it's really easy to find such vectors. And that's why the annulus is orientable. So there is a consistent choice of coordinate system that doesn't change its direction, but on a Möbius strip you can't. And as soon as you have a surface where you can't do that, you call it non-orientable. And that's the whole point of the definition. And whenever you can do this, I have another example for you. Let's look at the sphere, for example. And we want to choose something that points somewhere. And now we move it around on the sphere continuously, let's say into the back, and then it points here. And we move it all the way to the bottom again, and it points by a miracle in the same direction. And on a sphere, you can always do that. No matter how you move, it will always point in the same direction. On a Möbius strip, you can't. On a non-orientable surface, you can't. This is not possible. And that's what makes it non-orientable. So there is no sense of direction if you want. Because if you specify one and turn around, then everything is twisted. So there's not really a sense of any direction. Let's try to do that on the Klein bottle, and it's again the same. So it points outwards. I have a slightly better picture here, I think. Need to pull it up. So it points outwards, it moves around, and then it makes this funny twist, and eventually it comes back to the same point, but now points in the opposite direction. And no matter what you do, you cannot avoid that happening. So this is a non-orientable surface. Right? So you cannot consistently choose a coordinate system on your surface. And that's what makes it non-orientable. For the Klein bottle, it is really the same. And it's the same problem. It doesn't really have an inside or an outside. We have seen that in several animations. Remember my little ant moving into the inside and then coming out again. So this surface has no inside or outside. And this is exactly the problem, because if you have something with an inside or outside, like the sphere, you can just say, okay, my direction here is point to the outside. And this will always work. So if you move around, it will always point to the outside and it will never twist itself. But here it does twist itself. Right. So these things do not, well, so Klein bottle and friends do not have an outside or inside. And we'll make that a little bit more precise in a second. Okay. Let me just give you an alternative description of this idea of orientation. So it's essentially this choice of a direction. So you take your hand, you somehow have a right-hand rule, you move around, let's say in a clock or something, and you can do that consistently. So if you come around, the clock was still the same, right? Clock moves around the torus and will come out the same in any direction. And that is not possible on an non-orientable surface. So on a non-orientable surface, so if you move around your coordinate system, your clock, whatever, so you move it around, let's say the green one, it moves around, moves around, moves around, moves around, and it comes out here and now contradicts into the red one, which is actually oppositely oriented than the green one itself. So you cannot consistently choose something. So if you would live on a Möbius strip and you would be right-handed and you walk around the Möbius strip, then you would turn out to be, you would still be right-handed from your perspective because you can't tell the difference, but everyone else wouldn't then think you are left-handed because everything changes. Left and right-handedness changes. Let me have an animation of this on the Möbius strip. So if you have you live on a Möbius strip and your friend stays where they are, and you move around, then you will turn out to be twisted compared to your friend. So for you, your friend will look twisted, but for your friend, you will look twisted. So do we do it again? So let's start again. So we start here. So your friend stays and you move out, okay? And you're both kind of the same, if you want, and you move around the Möbius strip and there's a stupid twist. And you come out again on the other side, twisted, right? So you and your friend are both right-handed. Your friend stays, you move around the Möbius strip, then your friend looks left-handed to you, and to you, your friend looks to your friend, you look left-handed. It's kind of really strange. So those surfaces are kind of really, really weird. So if our world would be such a surface, then you could change the turning around of everything. This is just extremely weird. It's kind of you move around the world and you change from left-handed to right-handed. And that's why those surfaces are so much more difficult than the other ones, because they have this extremely absurd property that you can't somehow specify a left and right on the surface. It's kind of a little bit strange. And we call them the jargon here, the formal name is that they are non-orientable. That's just what we say. They are non-orientable. Fine. Okay. So we need kind of a criterion to check whether something is non-orientable. So I tried to, well, this was kind of our motivation. And you can prove, I won't do that, but I could prove that this one is equivalent to having a Möbius strip. And I did those manipulations here, for example, on the projective plane to show that the Möbius strip appears. The projective plane has no sense of left or right, but you somehow need a little bit of a better way of doing it. And here's a really, really fantastic theorem with a not too difficult proof, which will do the job. Namely, if our surface is a real-world object, what is a real-world object? Let's say it embeds into the space, like a torus, like a swim ring, a soccer ball, a sphere, an annulus, which is just a pipe. So all of these live in our space. And yeah, so, and all of these are orientable. So kind of nature prefers orientable things because they're exactly the ones that fit perfectly into a real space. And I will show you the proof. It's not super difficult. It's essentially just saying you have an outside and an inside, and whenever you have an outside and an inside, you have a preferred way of saying, well, there's a normal vector which points in a certain direction. You simply can't do that on a non-orientable surface. Okay, this is our real-world theorem, if you want. The non-orientable ones, difficult to think about. They don't exist in free space. You might wonder now, the Möbius strip does exist in free space, but here I have this condition without boundary. So I'm thinking about a Klein bottle or projected plane here. You cannot put them into free space. They're non-oriented. Because if you could put them into free space, they would be oriented. And here's essentially the proof. And I have a little sketch of what's going on. Also, I do it in 2 dimensions because it's kind of easier to illustrate in 2 dimensions. I will try to draw a picture in 3 dimensions as well. So let's say we do the following. So we have our sphere here, and we want, and now it lives in 3 space. Here's our 3 space, and we have our little sphere. So what we do is we choose some point that I call omega, very far away, and then I should race at my sphere. So let's say this ray doesn't hit the sphere, so I give it coordinate 0. And maybe I go into the sphere, so here into the sphere, then maybe I give it coordinate 1 because I've cut the sphere once. And maybe I go into the sphere and then out again, then I would give it coordinate 2 because I've cut the sphere 2 times. And yeah, I hope that's kind of clear. I shoot kind of lasers at my sphere and I kind of count how often I hit the sphere. Whether I don't hit it, it's 0, or I just hit it once, that is 1, or I hit it twice, or I hit it whatever, 15 times. I just write down the numbers I hit my sphere. So let's do it here. Maybe this is just a plain picture. Maybe that's easier. So I have my point omega, and I shoot it inside. So I hit the surface once, I cut it once, so I write down 1. Well, if I don't hit it, I write down 0. If I shoot through, I enter and exit, so I write down 2. Here I enter and exit again because I end up in the hole, so I write down 2. here I go through the hole. I first enter it, then I go out to the hole, and then go in again. So I write down 3, and so on, right? So for every point, I can write down a number. How often, from my starting point, I shoot a laser at that point and kind of note how often I hit my surface. And I just call the ones, you can already see it here, that have an even number. I just call this the outside. And everything that has an odd number, I just call it the inside. And I have V in and V out. Right? So that's what I do with my sphere as well. I have my little sphere, and I just, let's say I have a point in the inside, and I shoot from here. So I hit the sphere once, go in, and then end at my point, so it's 1. If I have a point at the outside, let's say would get 0. So everything even is outside, everything odd is inside. And I'm really using that it lives in 3 space here, because I just fix a point and shoot at my surface. In particular, R3 is now a disjoint union of my surface, the inside points and the outside points. In particular, I can say that my surface has an inside and an outside, namely the corresponding inside points and outside points. So, and this really kind of makes sense. And what you can do now is you can move along the inside or the outside and write down this coordinate system. I've written that down, and you would come to a contradiction if it would contain a Möbius. But anyway, the point is, I just written it down formally, but the point is really, as soon as you have a notion of an inside or an outside, you can put kind of an orientation on your surface by just at every point you point, for example, to the outside points instead of to the inside points. And that's kind of a proof that every surface lived in 3 space is actually oriented. And I put up the statement again because it's kind of really important. So this is really our real world theorem. So that's why all these surfaces, like the donut or the pair of pens or the soccer ball, why they all look so familiar, because they appear in the real world. And why the other ones look so strange, because they cannot appear in the real world. You cannot build them in 3 space. Kind of really interesting distinction. So essentially you can think of orientable versus non-orientable as being whether you can put them in 3 space or not. It's kind of a really interesting way of doing it. Okay. Yeah, that's exactly the point. If it's non-orientable, it does not embed, and if it's orientable, it actually lives in 3 space. So it's kind of really nice thingy. And this is again related to our little friend, the Klein bottle. So if you remember how it works, we somehow can't build this in 3 space. And now we have a good way of saying we can't because it's non-orientable. So we really can't do it. Yeah? So you can never do it. It's not like this illustration can't do it, but you can really never do it. It's not an object that could appear in the real world, which I think is a really cool statement. Yeah. So really, it has no inside, it has no outside. So this liquid, you can actually, if you build them out of glass, which is kind of cheating because it self-intersects, so it doesn't live in 3 space. So there's the self-intersection here. But anyway, you can buy them on Amazon or something and build them out of people have built them out of glass, and you could fill a liquid inside, but you actually can't. So there's no inside and outside. It just stays there because of the shape of the surface is a little bit wild anyway. So strictly speaking, you can have an object, and yeah, it's not that expensive. If you want it, you could buy it on Amazon. You can fill water inside, and it's still not inside. It's kind of very strange. Anyway, so you can't do that actually, but in practice you actually can. Yeah, just a fun fact. So let's wrap up this lecture. So in case this was too much waffle and you already forgot what we want to do, orientability is our 3rd point on the list. As soon as we know Euler characteristic, boundary cycles, and orientability, we can determine the surface. Okay, but we will see that later. I take a slight detour now because we are already in this in and outside thing, and I show you something really fantastic. So essentially, you should think of the nice surfaces as the ones with in and outside, and the non-orientable surfaces, the difficult ones, the ones without in or outside. Okay, and we can ask the same, and this is actually really difficult. So we could ask the same for curves in R2. So I could draw a curve here, whatever, and I could ask, does it have an in or an outside? And you would say, yeah, of course it does. So here I can mark my inside red, for example, yeah, and my outside is white. So there you go, there's an in and an outside. But is this actually really clear? Turns out that for general curves, this is like really difficult in a certain sense, and it has a name. So it's called the Jordan curve theorem. So every curve that you can ever draw in the plane has an in and an outside. And I will show you now, it's really amazing. I will show you now why this is so difficult to prove, because those lines can get really difficult. Okay, so for a line like on the right-hand side, it's really simple. Of course, it has an inside and an outside, an interior and an exterior. Just really, really easy. But what about this guy here? A little bit more of a complicated curve. Is there an inside and an outside? I somehow can't tell. Even looking, staring at it, it's a little bit difficult to say. The Jordan curve theorem tells you it does. So let me show you a slightly better way of seeing that it has actually an inside or an outside, and your computer knows how to do that. So I just open the picture itself with a tool that can change pictures. So this is exactly the same slide as before, just I have a slightly different tool. And now I shall show you a cool trick to determine whether this has an inside or an outside. I just use the fill tool, and the bucket fill will show us inside and outside. Takes a while, but there you go. It has an inside and an outside. So it found it actually. And you can always do that, so your bucket fill will never fail you, is essentially the Jordan curve theorem. Let's do it again. I can't quite tell whether there's an inside or an outside, but bucket fill, I could just, maybe I do it here, will never fail me, and it will find, there you go, it found the outside. If I would have clicked a little bit further here, it would have found the inside. Fine. But the bucket fill works is actually an instance of the Jordan curve theorem, which is kind of a fun thing to think about. And really, those curves get really difficult. Like here, it's a really beautiful picture of a curve where I again can't really tell whether it has an inside or an outside. But homework, just use bucket fill, and you will actually see that it works. And the formal statement, you could prove that. We won't do that. The proof is a bit difficult, but you can prove that. And the formal statement is called the Jordan curve theorem, or that we rename it into the bucket fill theorem. Okay, so that you can always kind of use the bucket fill button, no matter how complicated your curve gets. That's essentially the Jordan curve theorem, right? So what we've done for surfaces was just a two-dimensional version of that. So the nice ones are the ones with in and outside, and where you could use bucket fill just in a higher dimension, and the more difficult ones are just insane. So if you would use bucket fill on the projective plane, it wouldn't work, for example. That's essentially what I'm trying to say. Never try to use bucket fill on the projective plane. Let me rather wrap up by telling you that everything else, so the orientable ones, soccer ball, swim ring, pair of pens, whatever, they all live in 3 space. All the other ones can be embedded in 4 space, which makes them so difficult to think about, because you need at least 4, but 4 is sufficient. So the projective plane cannot be embedded into R3, but it can be embedded into R4, and I actually did it here in coordinates, in case you wonder how that works. As usual, I encourage you not to look at coordinates, but anyway, I'm just saying it works. And turns out that everything is built from every non-orientable one is essentially built from a projective plane or a Möbius strip. So we could put everything in 4 space, right? So non-orientable surfaces can be constructed from projective planes. That means that every non-orientable surface embeds into 4 space. That's really the difference. 4 space for non-orientable ones, 3 space for orientable ones. 3 space, the easy ones, 4 space, the difficult ones, right? That's why it gets so difficult to imagine them, because you somewhat need 4 dimensions to do it, right? And that's just a little bit too much, at least for my brain. Right, so every orientable one was in 3 space, and the non-orientable ones were at 4 space. So here, this one is 4, and this one is 3, right? And this kind of really makes a huge difference how difficult it is to imagine them. And that's the usual problem, like projective plane is really difficult to imagine, while it naturally lives in 4 space. So that's why it is a bit difficult to kind of wrap your head around. Okay, so that was the topic for today. I showed you non-orientability, so let's go all the way back to the beginning. It's probably faster if I do it like this. So we have this question mark on the first slide. What is the third ingredient we need? And it turns out the third ingredient is essentially orientability, and we'll see that in the next few lectures. So what do you need to, and it's pretty amazing then, what do you need to do in order to check whether two surfaces are homeomorphic? Compute the Euler characteristic, compute the boundary cycles, and check whether it's orientable or not. And I showed you during this lecture, maybe around here, it was too much, maybe around here, I showed you this theorem that orientable surfaces live in 3 space, and kind of in the opposite, maybe around here, yeah, almost, we will have seen that non-orientable surfaces actually need one more coordinate. And we are going to explore that further in the next video. But for today, that's it. So thank you so much for coming, and enjoy the rest of your day.